You know all those apps you use every single day? From streaming your favorite show to sending a quick message, building them is a massive, kind of daunting challenge. It seems impossibly complex from the outside, but here's the secret. Behind the curtain, it all follows this surprisingly logical, almost elegant blueprint. This is the blueprint that powers our entire digital world. So let's dive in and see exactly how it works.
Think about it. You type a message, you upload a photo, you hit play on a video, and it just works instantly. It really does feel like magic, doesn't it? But it's not. What's really happening is a carefully choreographed journey that your one single request takes through an incredible digital machine. And today, we're going to follow that one request on its journey from the moment you tap your screen to the very end. And this is our map. Okay, whoa. I know, it looks overwhelming at first, and that's kind of the point. It shows the whole intricate landscape of a modern application. But don't worry, we're going to break it down. Just think of this like a city map. We're going to follow one little car, our request, on a tour through the city, and we'll stop at all the key landmarks to understand what they do.
So our journey begins right here, at the city limits. This is the very first point of contact, where your request, coming from your phone or your laptop, first arrives in the application's world. But before it can get inside, it's got to do two things. Find the right address and get past the front gate.
The very first step is just figuring out where to go. See, you type in a website name like google.com, but computers, they don't speak in names. They speak in numbers, these things called IP addresses. So DNS is basically the universal translator. It's the internet's giant address book that looks up the name you gave it and finds the exact numerical address your request needs to travel to.
And as you can see here, it's not just a simple one-step lookup. It's more like a really quick conversation. Your request first asks a root name server, hey, where do I find anything that ends in .com? That server points it to another one, the top-level domain server. From there, it asks for the specific domain, which finally gives back the exact IP address from the authoritative name server. It's this super fast, hierarchical search just to find the right destination.
Okay. So once our request knows the address, it arrives at the front entrance, where it immediately meets the traffic cop, the load balancer. A really popular app might have hundreds of identical servers all running at the same time. The load balancer's only job is to look at all the incoming traffic and spread it out evenly, often using a really simple rule called round robin. It's just one for you, one for you, one for you. This makes sure no single server gets totally buried in requests.
After getting directed by the traffic cop, our request finally arrives at the API gateway. Think of this as the official front door and the security guard all rolled into one. It checks your credentials, it makes sure you actually have permission to enter, and it acts as this single, clean entry point to the dozens or maybe even hundreds of different little services running deep inside the application.
All right, our request made it past security. We are now officially inside the core of the system. Welcome to the engine room. This is where the real work gets done, where data is read, written, and processed to make the app actually do its thing.
At the absolute heart of any application is its data, and that data lives in databases. You can think of them as having two main flavors. First, you have relational, or SQL databases. These are like perfectly organized spreadsheets with really strict rows and columns, perfect for things like user accounts or financial transactions. Then you have NoSQL databases. These are way more flexible, kind of like a digital corkboard where you can pin up a bunch of different documents. They're great for less structured stuff, like social media posts.
Now, constantly going all the way to the main database to get information can be pretty slow, and that's where caching comes in. A cache is basically the system's short-term memory. If tons of people are asking for the same exact piece of data, like a viral video or a celebrity's profile, the system is smart. It keeps a copy of it in a super fast, easy-to-reach place called a cache. This is what makes an app feel incredibly snappy and responsive.
And engineers have a whole toolkit for this. It's not just one thing. They can store the cache right inside a server's memory for lightning-fast access. For massive scale, they can spread that cache across a whole network of machines in what's called a distributed cache. They can even tell your own web browser to hold on to certain files so you don't even have to ask the server for them a second time. So modern applications do way more than just fetch simple little bits of data. They have to handle huge video files, send out millions of notifications, process payments, and for all these really complex jobs, you need specialized tools and some pretty clever workflows. Let's take uploading a video. Trying to send one giant file is super risky. If your connection drops for even a second, you might have to start all over again. No way. Instead, the system uses a really smart chunking strategy. Your phone actually splits the video into a bunch of small pieces. Then, it asks the server for a unique, secure upload link for every single piece. It uploads all these little chunks at the same time, and once they've all safely arrived, the server just stitches them back together. It's way faster and so much more reliable.
This slide shows a really powerful concept for handling complex stuff efficiently. Imagine you buy something online. That single action, clicking buy, needs to do a bunch of things, right? It has to trigger a payment, update your order history, send you a notification, and log the purchase for analytics. Instead of having one giant, clunky service try to do everything, the system simply announces, hey, a purchase event just happened. Then, all these smaller, specialized services, one for payments, one for notifications, and so on, are all listening for that event, and they do their specific job independently. This fan-out model is how these systems can handle millions of actions at once without breaking a sweat. So, we've seen the individual components, but what are the guiding philosophies behind all of it? Let's zoom out now and look at the high-level principles, the rules of the road that architects use to make sure this whole complex city actually works and works well.
These are the big goals that every system architect is aiming for. Scalability. Can it grow to handle 1 million users or 10 million? Performance. Is it fast? Does it feel responsive? Security. Is it safe from attacks? And fault tolerance. What happens if one part breaks? Does the whole city shut down? To get there, they rely on key strategies like modularization, breaking the whole system into small, independent services, and abstraction, which is all about hiding the complexity to make the system easier to manage.
And this brings us full circle, right back to our original map. But now, hopefully we can see it with new eyes. Every single component we've talked about, the load balancer, the caches, the databases, was chosen specifically to serve those core principles. The load balancer is there for scalability. The cache is there for performance. The API gateway is there for security. It's a really complex system for sure, but every single part has a very clear and distinct purpose.
Ultimately, this isn't just a technical diagram. It's the fundamental blueprint for how we connect, how we shop, how we communicate in the modern world. It's the hidden anatomy of the apps that basically define our daily lives. We've seen how it all works today, which leaves us with one really exciting question. What incredible new systems will be built on these same principles tomorrow?